Yes, hi again. My name is Lukas Aumayr, and today I will present to you Blitz. This is a joint work together with Pedro, Moreno-Sanchez, Aniket, and Matteo, Maffei. And this work is accepted to this year's Usenix Security Symposium. So what is Blitz? Blitz is a new multi-hop payment paradigm for payment channel networks that is more efficient, reduces the collateral lock time from linear to constant, reduces the contract size, and is more secure against certain types of attacks compared to current payment channel network payment solutions. Let me begin by giving some motivation and background. So why do we actually care about this? As most of you might know, Bitcoin and other cryptocurrencies have an inherent scalability issue. So we have the blockchain, which is a global distributed data structure that records every transaction that is done in the network. And on top of this, we have a global consensus through which everyone checks the whole blockchain in order to verify transactions. And this, among some other things, highly limits the transaction rate of cryptocurrencies. So if we, for instance, look at Bitcoin's transaction rate, we will see that it manages only about tens of transactions per second, which is not a lot if we compare it to more centralized systems such as Visa, which can handle peaks of tens of thousands of transactions per second. So it's a quite big difference. One approach to solve this is actually to move off-chain and not record every transaction on the blockchain. Instead, we keep most of them off-chain and use the blockchain mostly for fallback in case of disputes. And among these off-chain solutions, payment channels have emerged as one of the more promising ones. And let me briefly now explain to you what are payment channels and how do they work. So assume we have two users, Alice and Bob, and these two users anticipate multiple payments between one another. So what they can do is they can open a payment channel as follows. They come together and they post one transaction on the blockchain that logs some of their individual coins into a shared output. Then from this shared output, they again create a new transaction off-chain that spends back their individual balances to them. This is the initial state of the channel, and the channel is then considered to be open. Once it's open, they can perform arbitrarily many payments between one another simply by creating a new state off-chain that redistributes the according balance according to the payment that they want to conduct. So they can go ahead, create multiple of these states, exchanging the balance back and forth until they are happy and wish to close the channel again. So what they can do then is they can go ahead and close the channel simply by sending the latest state again to the blockchain. So notice that even though they can perform arbitrarily many payments between one another, only two of them actually are captured on the blockchain. Of course, now maintaining a payment channel with every user you potentially want to interact with requires you to lock up a lot of funds, and this might not be feasible. So instead, it turns out we can actually go ahead and take payment channels and link them together to form a payment channel network. And in such a payment channel network, any two users that are connected via a path of channels can perform a payment between one another. And then probably the most prominent example of a payment channel network is the Lightning Network. And we can see by looking at some current numbers that this is actually used in practice. So there is like $53 million worth of Bitcoin locked in the Lightning Network. There are around 21,000 nodes and 46,000 channels in the Lightning Network. And now let me briefly go over how the payments currently work in the Lightning Network. So assume the following scenario. We have Alice who wants to pay 5 coins to Dave via Bob and Carol. So there's a channel between Alice and Bob, between Bob and Carol, and between Carol and Dave. So what they do is they go ahead and Dave samples a random pre-image X and sends Y, which is the hash of X, to Alice. Now Alice goes ahead and sets up an HTLC or hash time lock contract with Bob, holding 5 of Alice's coins. And an HTLC is nothing more than a simple smart contract that can be scripted with the rather limited scripting language of Bitcoin and encodes the following logic. So Bob will get the 5 coins that Alice put if he knows X, such that X hashes to the condition Y, and Alice can get back her money after some timeout. In this case, it's 3T. Now, Bob will go ahead and also set up an HTLC with Carol, and Carol will set up an HTLC with Dave. Now, of course, Dave knows the pre-image X, so he can redeem the HTLC with Carol, excuse me, by revealing X and thereby claiming the 5 coins that are locked in the HTLC. By doing this, Carol will also know the pre-image X, and she can go ahead and redeem the coins that are locked in the HTLC with Bob, and Bob can do the same with Alice. And now the payment is successful. Let me point out some important points of these types of payments. The first one is that these types of payments require 2 rounds of communication. And by round of communication, we mean a sequential and pairwise communication from the sender to the receiver or the other way around. And indeed, we can see that we require this round 1, in which we lock up the money, and then the round 2, in which we release the money again. And we also dub this the 2-phase commit scheme, because it is not unlike the 2-phase commit schemes that are used in distributed databases. Another thing I want to point out is that these types of payments require a staggered collateral lock time, meaning that the lock time is linear in the path length. And why is this the case? So normally in the case that we have honest users, the payments are settled off-chain. So what they would do is, for instance, Dave and Carol would go ahead and so Dave shows Carol the pre-image X, and they would honestly update their channel to represent the new balance where the 5 coins have moved from Carol to Dave. But of course, there might be the situation where someone has to forcefully claim the money from the HTLC on the chain. And in order to ensure that the intermediaries have enough time to react to such a claim in their right channel, we need to increase the timeout of the HTLC in their left channel in order to ensure that they have enough time. And here, as you can see in this picture, the timing grows from T to 2T and to 3T. All right, so now let me go over some of the other properties and drawbacks of Lightning payments. So one thing is the Lightning Network actually is a solution to the scalability issue that I described in the beginning of the talk. It also achieves, so Lightning payments achieve balance security, which means that honest users that participate in the payment cannot lose coins. And the third thing I want to point out is that the Lightning payments achieve privacy in the sense that in an optimistic payment, the intermediaries will only learn about the direct neighbors and the value that is being sent, but they won't learn, for instance, about the whole path in the case of an optimistic payment. However, there are also some drawbacks in Lightning payments. For instance, as I already mentioned, we have this staggered collateral lock time, meaning that if a payment fails, then the collateral will be locked for a time that is linear in the path length. And payments can fail for different kinds of reasons. Users can go offline. There could be malicious users. So for instance, there is actually an attack, the griefing attack, that lets, where adversaries potentially let payments fail in order to decrease the network throughput, or there could be some other errors. And due to the fact that the time is, the collateral is locked for a time linear in the path length, this can lead to a decrease in the network throughput. Another thing is that, as I mentioned, this scheme takes 2 rounds of communication. Additionally, we require HTLC scripting to be supported in the underlying blockchain. And finally, these types of payments are susceptible to the wormhole attack, which is an attack in which honest intermediaries are cheated out of their fees. So let me now go over the Blitz construction, which achieves all these properties, but also improves on these drawbacks. And the way I will present it is I will start by giving a simple way of doing payments in one round, point out some problems with it, and then incrementally improve it until we arrive at the solution. So let's start with a simple first attempt of doing one round payments. So again, we have the scenario where Alice wants to pay 5 coins to Dave via Bob and Carol. And a very simple approach could be one where, okay, Alice and Bob, they go ahead and simply update their channel such that the new channel state, in the new channel state, Bob has 5 coins more than before. So actually, in the new state, Bob received the 5 coins from Alice. After this has been updated, Bob will go ahead and update his channel with Carol in the same way, such that the 5 coins move from Bob to Carol. And then Carol will do the same with Dave. So they all honestly update their channels, the coins move from left to right, and the payment is done. And this is actually used in the interledger payment scheme. Of course, we can see that this might cause some problems, especially if we have intermediaries that can be malicious. So one thing that could happen, for instance, if we have a malicious Bob, what he could do is simply stop the payment, so he does not forward this to Carol, and he will effectively have stolen the 5 coins from Alice. So this is not good. So what we will do to try and solve this is the following. So we can try and introduce a refund mechanism to this scheme. Okay, so what does this mean? So Alice will now, instead of updating the channel with Bob directly to the state in which Bob gets the 5 coins, update the channel with Bob to an intermediary state that holds the following contract. After some time t, which is chosen by Alice, Bob can claim the 5 coins that are locked in this contract, right? Before time t, however, Alice has the way to refund herself. Okay, now Bob goes ahead and does the same with Carol. So he creates the same contract, and Carol does the same with Dave. Now Dave can send back a confirmation to Alice where he says, look, Alice, I received this payment, so it's actually fine. And Alice will go ahead and simply go idle. And after the time t expires, the money will move from left to right in each channel. If she doesn't receive the confirmation, Alice can go ahead and step back from the payment by simply publishing the refund, and the subsequent users will follow. Of course, this scheme now has 2 problems. So the first one is that the way it is shown here, everyone can trigger this refund. So what we actually want is that only Alice can trigger it, right? So I mean, if Alice deems the payment successful and goes idle, she doesn't want that Bob, for instance, posts a refund. And the second thing is that the timing is the same for everyone. So if the refund is posted at the last possible moment, the other parties might not have time to react. So indeed, what could happen here, again, we have a malicious Bob. And even though the payment was actually successful, Bob goes ahead and publishes the refund just before the time t expires. And the others won't have time to react. So in the other channels, the payment goes through. And in this case, Carol will have lost the 5 coins and Bob will have stolen them. Right. So there would be one way how we could solve this, and this is the following. We could introduce again some hash condition where this time Alice chooses a pre-image and all of the refunds are conditioned on this hash condition, right? This prevents that anyone but Alice can trigger the refund. And in order to solve the problem of the time, we could again introduce some staggered time so that grows from left to right in this case, in order to ensure that if someone refunds in the last possible moment, then the user on the right will have enough time to react and refund themselves. But of course, this doesn't solve what I promised you earlier. So this requires the same scripting requirements as the Lightning payments. And again, we have a collateral time that grows linearly. And also for instance, for the refund case, we would have, again, this more or less this second round. So it is, again, sequential in a sense. So instead, we came up with the following, and we dubbed this solution the PairRevoke paradigm. And the way it works is as follows. So we have Alice, who defines a timeout t, which is similar to the timeout t from the last slide. So it's a constant time in the future, and it is independent of the path length. Following, Alice creates a refund enabling transaction TXER that contains an output belonging to each of the users on the path, except for the receiver Dave. Right. Now Alice goes ahead and creates the following contract with Bob. And this contract looks similar to what I've shown in the last slides. So again, after this time t chosen by Alice, Bob will get the money. But before time t, Alice can refund, but only if the transaction TXER was published before by Alice. And the way this can be done is simply by using this output in TXER that belongs to Alice as an input for her refund transaction. Right. After this, Bob will go ahead and create the same with Carol, and Carol will go ahead and create the same with Dave. Now Dave goes ahead and sends back a confirmation of the TXER that Carol used in their channel for her refund transaction back to Alice. And now there are two different ways. So either the confirmation is a correct one, meaning that the TXER that Dave sent back to Alice is the one that Alice created in the beginning. And in this case, Alice can simply go idle because she can be sure that after the timeout t expires, Dave will get the money. And this is because Dave sent back this confirmation that ensures Alice that the refund that Carol uses in the channel Carol Dave is dependent on Alice publishing TXER. So if she doesn't publish it, that means that the money will go to Dave after this time t. Right. The second case is, of course, that Alice does not receive the correct confirmation, or she does not receive a confirmation at all. In this case, Alice will post the transaction TXER in time before the timeout t expires, and everyone on the path sees this at the same time and can react and refund themselves. Right, so note that this payment scheme takes only one round of communication. Okay, there are some other improvements for these payments, which unfortunately I don't have time to go over them in detail, but I will just mention them here. So remember that the time t is constant, so it's independent of the path length, and it can be relatively short. However, in the case that there are only honest users, you still might not want to wait until this timeout t expires, which is why we introduced the fast track for payments. And this is an optional second round of communication for efficiency reasons, which we can use to achieve also these instant payments, similar to what we have also in the Lightning network in the case of honest payments. The second thing is a fast revoke, which allows the users on the path to refund themselves or to revoke the payment without requiring to post the transaction TXER or without actually requiring to post any transaction on chain. And this is actually important for instance, if you set up a payment and there is not enough balance for this payment, a user is offline and the users simply want to revert the payment. The third thing is that we can achieve the same privacy as the Lightning network by introducing stealth addresses in the outputs of TXER, and thereby we can again hide the path of the payment except for the direct neighbors of the intermediaries. And I encourage you to check the paper for more information on this in case you're interested. Now let me move on to the evaluation. First, let me compare this to some current payment solutions. I've already shown you this interledger payments, the ILP, which actually achieves the payments in one round, but of course it doesn't have the balance security. So also we have the Lightning network, which does achieve balance security, but again, the Lightning payments require 2 rounds of communication, require collateral lock time that is linear, and it is also susceptible to this wormhole attack that I briefly mentioned. The next thing is this AMHL, or the anonymous multi-hop locks, which unfortunately I can't really go over in detail, but this is an improvement on the Lightning that makes them secure against the wormhole attack, more or less. And finally, our construction, it achieves the balance security. It has this 1 round constant collateral and is also secure against the wormhole attack. So now for the evaluation. So we actually did 2 kinds of evaluations. In the first one, we created the necessary transactions for the Blitz payments. And we actually noticed that the contracts used in Blitz are 26% smaller than the Lightning contracts, or the HTLCs. And this can lead to an increased number of concurrent payments per channel. So why is this the case? So the channel states are stored in transactions, and transactions have a limited size. And of course, the outputs, so the outputs of this transaction, they can represent the concurrent payments. So if we decrease the size of the contract of these outputs, as you see in this small figure, we can actually fit more payments into one transaction. So this is why we could increase the number of concurrent payments in practice. The second thing is we did a simulation in order to showcase the advantage of having constant collateral over staggered one. And for this, we took a Lightning network snapshot and we created some random payments on it. And some of these payments are disrupted, which means they fail for some reason, either due to some errors, users being offline maliciously, and so on. And the failed payments, the collateral of them is locked either for constant time in Blitz or for staggered or linear time in Lightning. And of course, collateral that is locked in a channel cannot be used for other payments. And then we ran the rest of the payments and we actually found out that depending on the setting, so actually how many payments are disrupted, how many payments do we send through the channels and what value do this have, we found that we have between 4 times and 33 times fewer failed payments in Blitz than in Lightning. Now to sum up, we introduced a new multi-hop payment paradigm, the PairRevoke, for payment channel networks. And in it, we achieve secure multi-hop payments in 1 round of communication. We reduce the collateral from linear to constant, reduce the contract size by 26%, and we are secure against wormhole attack. On top of this, we require only signatures and time locks, so we don't actually require hash locks. We did a simulation to show the practical advantage of having constant collateral. We formally modeled the protocol in the universal composability framework and gave security proofs. And let me finally mention also that the payment scheme is also compatible with current Lightning network channels. So thank you for your attention, and I'm looking forward to some nice questions. And here are also some ways of contacting me.